Okay, so today is the second part in talking about spontaneity, that you're now thinking about it as something being thermodynamically favored. And we've talked about the two factors that determine so far that you know about whether something is thermodynamically favored or not. And they're the enthalpy change and the entropy change for the system. So if the enthalpy change, delta H, is the difference between the sum of the internal energy and the work energy, the products and the reactants. If something is thermodynamically favored, what is the sign of delta H?
Negative.
Negative, and that would be an exothermic or endothermic reaction? Exothermic. And then the entropy change, delta S, is the difference in the randomness of the reactants compared to the randomness of the products. If the entropy is positive or negative, is it thermodynamically favored? Positive. Positive. The more disordered, the happier the universe is. Now, let's talk a little more about enthalpy. Enthalpy is usually measured in kilojoules per mole. That's going to be really important to you on Monday when you get the problem wrong, because everybody makes the same rookie mistake. Stronger bonds mean more stable molecules. Okay, what would a strong bond be? Anything that is a...
Hydrogen. Or would it be the hydrogen? Would be like ion.
Okay, we've fallen into the trap. The intermolecular forces, the forces that are keeping two molecules together, would be hydrogen bonds and London dispersion forces. And dipole-dipole, right? Mm-hmm. Now, the stronger bonds that I'm talking about are intramolecular bonds that are actually holding the molecule together. So what I'm talking about in this case would be a single, double, or a triple bond. Okay, and the triple bond would be stronger. Okay. So you know that when a reaction happens, you must put energy into the reactants to break the existing bonds and to allow them to reconfigure, and when they reconfigure into the products, energy is released. Okay, so if the bonds in the product are stronger, more energy is given off when they form, and that would be more spontaneous because it would be leading to an exothermic reaction. If the bonds in the products are weaker than the bonds in the product, that means that it's endothermic and that is not thermodynamically favored. Okay, so now we are pretty clear on that, I hope. And now let's talk a little more about entropy. Entropy is, okay, stop that. Entropy is measured in joules per mole. Joules per mole. Circle that. It's the odd one. When you have a process, that means chemical reaction, where the final condition, that means the products, is more random than the initial condition, that means the reactants, the delta H of the delta S of the system is positive. This is another way people write delta if they can't format it on their computer. So if you see DS, that's not a gaming system, that means delta S. Okay? And if the entropy change in the reaction is positive, that is thermodynamically favored because the universe likes disorder. For a process where the final condition is more orderly than the initial condition, that means the products have less disorder than the reactants did, that will be a negative condition, and it is not thermodynamically favored at that point. So we talked about the 0th law of thermodynamics yesterday and the first law of thermodynamics yesterday. The 0th law of thermodynamics had to do with a man in a snowbank, yes? And we talk about that, and that means that heat always flows from hot to cold. And the first law of thermodynamics is that energy is always conserved, yes? Okay, now we're going to talk about the second law of thermodynamics. The second law of thermodynamics says that the total entropy change for the universe must be positive in order for the process to be spontaneous. One more time, the universe is composed of two parts, the system and the surroundings. Okay. And so you can look at it like this. The universe is equal to the system plus the surroundings. For a reversible process, the change in the entropy of the universe is zero. Is zero. Why is that so?
It doesn't change, it changes back and forth.
Right, it's ping-ponging back and forth between the forward reaction and the reverse reaction. Forward reaction and the reverse reaction. For an irreversible or a spontaneous process, the delta S of the universe, by definition, must be positive. Name me an irreversible chemical reaction that you know of.
Rust.
Rusting. Yep, rusting. So it rusts spontaneously without outside intervention. It does not unrust. That'd be great if it did, but it doesn't.
Make it, like, get rid of the rust. Make a
Well,
little spray
navel
can.
jelly, and does anybody know what that weird stuff is? I always forget chemically what it is, but it looks like orange goo, and you put it on rust, and you have a little side reaction, and the rust goes away.
I did do stuff like bows, like they put copper plates on like ends of like ships that like oxidizes instead of the rest of
The rest of it?
Yeah,
Oh, that's a good idea.
or something like that.
It's more reactive than the metal
Yeah, I
that
guess
it's
like all
made of.
this stuff happens to the copper as opposed to the hull of the ship, so it doesn't rust away.
That's a good idea. I bet you they thought that was a good idea, and that's why they do it. Okay, let's talk about this. This is kind of difficult for you to wrap your head around, but here we go. If the entropy of the system decreases, then the entropy of the surroundings must increase by a larger amount in order for the reaction to be spontaneous. Because by definition, if it's spontaneous, the delta S of the universe must increase. So if this is a negative value, this must be positive to cover that negative and then some. Got it? Okay. So when ice is placed in water, heat flows from the water to the ice. According to the second law, heat must flow from the water to the ice because it results in more dispersion of the heat. And the entropy of the universe therefore increases. So the second law demands that the entropy of the universe increase for a spontaneous process. Even though spontaneous process like water condensing and happen spontaneously, even though water vapor is more entropic, I just made up that word, has more entropy than liquid water, it does occur. Why?
Some flow of energy.
Been a really large increase in the entropy of the surroundings. The system in that case would be the water, and that would be a negative value for that entropy going from a vapor to a liquid, but the surroundings is getting a boost there as well. The third law of thermodynamics says the absolute entropy of a substance is the amount of energy it has due to the dispersion of energy through its particles. Strictly stated, the third law of thermodynamics says that for a perfect crystal at absolute zero, the absolute entropy is zero. Let's think about this. When we talk about a perfect crystal, that means that it has some lattice structure, and at the lattice points are some atom, molecule, something. And it is perfectly ordered. A perfect crystal would be so geometrically lovely that it has zero potential energy. Do you get that? It isn't, because of the placement of its particles, it has no potential energy. At absolute zero, the temperature is, and we define absolute zero as the temperature at which all kinetic energy stops. All motion stops, therefore all kinetic energy is zero, yes? So the third law of thermodynamics, the way I'm looking at it, says that the PE, the potential energy, is zero, and the kinetic energy is zero. Therefore, the entropy is zero. Got it? So therefore, every substance that's not a perfect crystal, every substance that's not at absolute zero has an entropy. So the absolute entropy for everything is always positive. This brings me up to something that you need to write on your notes. If you thought about this, the delta H of formation, that's the change in enthalpy when a element or compound or molecule is formed at standard conditions. That ought sign means standard conditions. In standard conditions are 25 degrees C, 1 atmosphere, and 1 molar concentration. The delta H of formation at standard conditions for all elements is 0. You will look on your thermodynamic chart and you will notice there are no values for any elements in the standard condition. Gibbs free energy of formation at standard conditions for all elements is likewise 0. The delta S of every element, compound, or molecule has a value. It has a value because it's not at absolute 0. Even if it were perfect crystal, it's not at absolute value, at absolute 0. So it does have some kinetic energy, therefore it has a value, and that value is always positive. I need you to write down one equation that you need for today's work, but we will explain more fully next week.